This video is a perfect illustration of how they use perspective to mathematically create their sphere.
Because you've got line of sight, if you've got three straight lines joining 3 points, then that's going to sum to 180.
And they weren't setting out to prove the shape of the Earth, but rather they were surveying to provide a framework for accurate mapping of the entire United States. So how to triangulation survey? The purpose of surveying is to establish precise locations of points within an area. With triangulation survey, it is done by measuring an angle from two known locations on our diagram, A and B, the baseline, to a third location and using trigonometry to determine the position of the third. And furthermore, the precisely measured baseline provides the starting point for the distance calculations. This method is well suited to covering large areas with a modest amount of effort using long chains of triangles. Triangulation itself covered the about 4,000 kilometres between Cape May, New Jersey, which is on the east coast of America, to Point Arena, California on the west.
Them yellow dots represent the only position where they measured the distance of one side of the triangle. And for hundreds of miles in between, they just used calculations based on the angles, which in reality make a very minute, negligible, if you will, in distance.
Now, it's important to stress that when they're measuring these angles, they are just measuring the horizontal angle, or in this diagram, what's called the azimuth angle between targets. The vertical differences are irrelevant between targets. It doesn't matter if one target is up on the top of a hill, the other one's down below them in a valley. It is just the horizontal component of this.
He just said the elevation doesn't matter. I'm going to show that it absolutely does matter, and how they are using perspective in calculating that into Earth curve. That's why they have to show you orthographic side-on Muppet vision. Even when talking about azimuth, look, they can't even show a straight-on azimuth angle. They still have to show you Muppet vision, man. That should be a dead giveaway.
One target is up on the top of a hill, the other one's down below them in a valley. It is just the horizontal component of the separation that matters. Now, this importantly means that refraction is not a factor in these measurements. Now, given that refraction essentially only happens in the vertical direction, and this is actually one of the reasons why I like using spherical excess as one. It's pretty much my favorite globe evidence.
So remember that, no refraction, so no excuse, and that's why it's his favorite proof.
Now, these are the measurements as published in the publication. Now, the thing I need to get a look at is the green box over here in the top left. Actually, yes, my cursor is showing, so I can show you. That didn't work. Hang on a moment. There we go, I got my highlighter going. So we can look over here in the green box here, and we can see that the angles of the Kent Island triangle, the one I was talking about here, add up to 180 degrees, 0 arc minutes, and 1.29 arc seconds. So we see that it does indeed add up to slightly greater than 180 degrees. But if we look down the page, we see, for example, triangle 2, triangle 3, and triangle 4.
Down the page, you mean the very next measurement, and the one after that, and then the next one after that, are all less than 180 degrees? I guess just error. Just error.
If we did a geodetic survey and we found no spherical excess, that would be evidence that the Earth was flat, right? But that's not what we find. When we do geodetic surveying, we find that there is spherical excess. It's not added in, it's not calculated.
In reality, they throw it out as error, and they can't use refraction, so that's out the window. Remember, that's why it's his favorite globe proof. But if we're going by that page of geodetic surveying, that proves the Earth is concave.
It's 5 add up to a little bit less than 180 degrees. Okay, which is a little bit of a problem. So you might think that this just makes the measurements a little bit inconclusive, a bit of margin of error, maybe, but there is actually a big problem if you think these angles are accurate, because planar triangles, flat normal triangles, sum to 180 degrees, spherical triangles always sum to greater than 80 degrees. So how can we have triangles that add to...
Gee whiz, he just writes it off as, wouldn't that be a problem if they're regular triangles? But line of sight can only ever give you 180 degrees. And when we survey, I've used the equipment my whole life, not surveying, but in leveling. And I've did long stretches before a few times. I've done miles of curve, I've done a seawall. Like, I've done a few big projects, but the point being is the ground doesn't matter. When we're using survey equipment, we're projecting straight lines. And the ground is of no significance. The ground is what we measure to, them straight lines. To see the slope. It's basically rise over run. If I drop 8 inches over a mile, I know that the water's going to flow that direction. That's not Earth curve. That's the way water's going to flow in reality. They do that every time their measurements don't line up with a sphere, which is always. Then they say, well, how would that work on a flat Earth? You know, on a flat Earth and in geometry, line of sight is going to give you 180 degrees for every triangle. Okay, so don't just throw out the ones less than 180 degrees. Throw them all out as error.
Now, I'll get to this explanation in a moment, but we're going to shift to somewhere else where this isn't quite so much of a problem. So
let's find some of the numbers that aren't a problem. We'll look for some numbers that do work.
just briefly before we go, if we look over here on the right of the screen, you'll see the distance of the sides of these triangles. It's in meters. So if we look at this first section, we've got 8, 13, and 11 kilometers. So
see, they only measured one side, and the other sides are calculations based on the angles. So of course they're going to, I mean, this is just, I mean, I don't get it. I don't know how they don't understand this.
Yeah. So I'm now showing similar things for the Salt Lake area. So Salt Lake, Utah. We're getting to the edge of the Rocky Mountains here. And if we look at the right-hand side here, we can see the triangles on this side have sides here of up to 185 kilometers. So they are significantly larger in this case. Okay, I can see my cursor highlights not coming through. It doesn't matter. I shall plow on. Okay, so now looking at the Salt Lake bassinet triangles with these big triangles, if we look at the red boxes on the left, I've highlighted again with little red boxes there, we can see that they have spherical excesses from these measurements of 6, 13, 33, 11, and 35 arc seconds. None of them have a deficit. We all have an excess of angles in those triangles.
That's funny. So when they start going up to like 150 kilometers or 200 kilometers, then they get excess on all of them. But over the short distances, they get mostly less than 180 degrees. I mean, wouldn't that form a pattern? So I'm going to show how perspective affects just a little bit, but enough, and how it affects. Because usually something farther away, it's going to be lower onto the horizon. So let me show you how that affects the angles, just enough. Now look at the solid black lines for the angle. Okay, the observer down at the bottom, and then the 3 elevations, okay, are all lined up, but with different elevations. Now let's say elevation 3 is higher, which represents usually closer. Okay, you're going to get a minute, but still measurable, slightly smaller angle. That's why up close they're getting less than 180 degrees. And look at elevation 1, it's wider, so you're going to get a little excess. There's something further and lower down to the horizon. It's just simple perspective, and it's not a big effect, but it is an effect. And so what they do is over the short distances, they throw out the angles that are less than 180 degrees. But, you know, in reality, line of sight, every triangle has to be 180 degrees. We don't see any curves.
Yeah, Zanik, if you have 3 straight lines forming this triangle, even if they're at different altitudes, it doesn't matter. If there's 3 straight lines between the points, then that must form 180 degrees.